this lecture we will be looking at another numerical method technique, that is, we will actually look at two. First, we will look at integration, how we can integrate a function. There are several methods for doing that. We will look at only one method, and you can, after that you can look up for other methods. Next, we will proceed to see how ordinary differential equation can be solved using numerical techniques, using programming. So, first of all, let us start with integration. Now, all of you know what integration means. Given a particular function, integration is, say I have got a function like this and I want to integrate, suppose this function is f x and I want to integrate it within the range a and b. So, we write that as integral a to b of f x, right. And you also know that this integration actually means the area that is under this curve, all right. This value is the integration. So, we will look at how we can solve this problem. The simplest, a very simple method is a trapezoidal method, which we will discuss here. So, you can see that, okay, let me go back to this this case. Now, you can see that I can approximate this curve in a very simplistic case using a trapezoid, right. So, I have got a trapezoid here. Let me draw in blue. So, the area under this trapezoid, this is red itself. So, the area under this trapezoid is approximating, under this trapezoid is approximating the area under the curve. But that is becoming possible here, except for this error, that is becoming possible here because the curve was very much not very skewed in that sense. But if the curve were something like this, that say it was something like this, and I was trying to integrate it between these ranges, then if I had fitted a trapezoid here, then the amount of error would be much more, because I will be committing errors at these points. Okay, I am not considering this, I am over considering these points, etc. So, the error will be more. So, it is not always the case that a simple trapezoid, one single trapezoid will solve, but let us start with that and try to understand how we can go ahead with the problem. So, the area under the curve in this particular curve, as you can see here, this particular curve that has gone through this is a trapezoid, under the curve is a trapezoid, this part. If I assume it to be a trapezoid, in that case the integral of f x dx is the area of the trapezoid, and we know that the area of a trapezoid is now nothing but half the sum of the parallel sides, that means f a plus f b divided by the height. Now, if I look at it, these are the parallel sides, then the height is this b minus a, this amount, right. So, this is a known result. Therefore, I can say if I can approximate a curve by a single trapezoid in this way, b minus a times f a f b plus f a by 2 or f a plus f b by 2. But of course, we will see that there can be errors due to this approximation, but this is a simple formula which we can quickly compute. It is very easy to write a program for that. You have got a function that will compute the curve. So, you call it for a and call it for b and compute this expression, you will get the integrand, okay, integral, all right. So, here is an example. Why is this important? Suppose the vertical distance covered by a rocket from time 8 to 30. So, my timeline is from 8 seconds to 30 seconds, is given by this formula. All right. So, the vertical distance overall total vertical distance is this. This is a complicated formula. Now, using single segment trapezoidal rule, let us try to find the distance covered. Let us try to find out the distance covered for this. So, we know for 8 and for 30, if I compute this function, this was my function. So, for f 8, my function is yielding this value, and for f 30, the function is yielding this value. We can compute using, you can use your calculator and find it out, that you need not do right now. So, you can compute the values at these 2 points, because this is the overall function. And next, so this is the f 8 and f 30. So, what will be my integral? My integral will therefore be 30 minus 8 b minus a f a plus f b by 2. So, that is coming to this value, sorry, that is coming to 11868 meter. The distance covered is this. But however, the exact value, if you compute it, the exact value, if you do a detailed computation, will be 11061 meter. So, there is an error. Obviously, there is an error because I have approximated the curve using a trapezoid. Now, let us see how great is the error, how big is the error. So, we can see that the true error is minus 807 meter, right, that is quite significant, 800 meters, and the absolute relative error, which is the actual error, true value and the computed value and divided by the true value, you find that I am getting 7%, more than 7% error. Okay. How can you better it? How can you better it therefore? So, our answer will be, we will, instead of applying a single fitting in a single trapezoid, I can try to fit in more than one trapezoid here, like something like this, that there is a trapezoid here, I fit in one trapezoid here, I fit in another trapezoid here, and I thereby I can approximate, I can minimize my error to some extent. So, here what we are trying to do, instead of taking 8 and 30 and fitting in one trapezoid for the whole thing, instead of fitting in one trapezoid for the whole thing, what we are trying to do is we are fitting in one trapezoid for 8 to 19, another for 19 to 30. Okay. So, now again using the same formula, we find then here is one 19 to 8 to 19, this is the integrand, plus the other trapezoid is giving me this. So, I am fitting in 2 trapezoids now, clear. So, if I do that, then let us see whether the result is being bettered. So, I compute f 8 at f 30 and f 19 and compute both of these values, the areas under the curve here and here, and the result is 11266 meters. Now, how far is it from the actual? Now, we can see that the true error is now has reduced from 807 meters to 205 meters. So, that tells us that if we can extend this procedure and fit in more and smaller, but more number of trapezoids, my error will come down further still. Taking cue from this idea, what is being done is the multiple segment trapezoidal rule therefore is that we divide into equal segments. Say here is one trapezoid, here is one, it is not coming here, let us see, select another color. Say here is one trapezoid, here is another trapezoid, here is another trapezoid, and here is another trapezoid. I am getting 4 trapezoids here and trying to formulate this. I can do that in this way. So, the integral is this whole thing, which will be a sum of these trapezoids. Remember, each these lines, this distance is the same. So, I am dividing b minus a by some particular value n, and that is my h. So, this is h, this is h, this is h, like that I am going for equidistant points and drawing the trapezoids from there. So, therefore, if I follow this as is shown in this way, the trapezoidal rule can be written as integral of a from a to b is sum of half f n plus 1, that is f a plus f b by 2 times the particular distance that is there, x 1 minus a, x 2 minus x 1, usually you do it in the equidistant mode. Okay. So, now multi-segment trapezoidal rule is therefore, and integral I can be broken down. This is simple. From a to a plus h, I can have f x dx, a plus h to a plus 2h f x dx, plus a plus n minus 2h to a plus n minus 1h f x dx, a plus n minus 1h to b. So, all the segments are being added together. Applying this, I get this formula b by a divided by 2n, because if n is coming 2 is coming n times. So, f a plus f b plus 2 into f a plus h, because that is coming twice, here once and here once. You see here f a plus h will come, here a plus h will come, right. Okay. So, using this, let us do the example again, the same thing. Using two segment trapezoidal rule, we could find that the error is coming down. We have already seen that the true value of error is coming down, and the absolute relative error has come to 1.853. So, now let us come to C programming straight away. How can we encode it using a C program? You see here, so I am reproducing the result here again. So, integral of f x dx between a and b will be h by 2 f a plus 2 f a plus h plus 2 f a plus 2 h. Why this 2 is coming? Because in the first zone f a and f a plus h, second zone f a plus h plus f a plus 2 h. So, each of these intermediate points are coming twice, that is why there is 2, and I have got this formula. Now, as a C programmer, your task is very simple. You see here that I have defined a n I whatever. I am asking the user for the necessary inputs, how many number of subintervals that you want to have, the initial limit a, you are reading the initial limit b, all those things you are reading. Now, the integral computation is done here. What is being done? H is, I am finding out the absolute value of b, because b and a, b minus a divided by n, and I am taking the absolute value of that, all right, because it could have gone on the other side also. So, now here I am just computing the sum. What sum? This part. What? Initially x is a plus I h sum plus f x. So, each of them, next time it is becoming 2, all those things I am adding here. So, here I am in a loop, I am doing a plus I h, initially I is 1. So, 1 h, 2 h, like that I am going on doing that, and ultimately and I am computing the sum here, sum plus f x. Now, note that f x is a separate function that has been kept somewhere here, and then ultimately I find the sum is these things, a plus h, this points. Now, integral is h by 2, this part, f a plus f b plus f a plus f b plus twice the sum, a plus h, a plus 2 h, a plus k h, like that. That part has been a plus I h has been computed inside this loop, and that I add with 2 here and here is my integral. So, that is the trapezoidal rule. It's the program is so simple if you understand the concept. Okay. Next, we will move to another very important engineering computation that is needed is solving ordinary differential equations. Quickly, let's all of you know what a differential equation is, and we will in particular look at Runge-Kuttas fourth order method, and here I will show examples that you can also find in this site of University of South Florida numerical methods, and I have taken the slides from them with the permission. Now, you see how to write an ordinary differential equation. Now, an ordinary differential equation you know is dy dx f x y. Okay. Now, dy dx, so how do I write it? I write it as, suppose this is something given, dy dx plus 2y is 1.3 into e to the power minus x, and what is this part? This is the initial condition. Okay. Now, this can be rewritten as by just changing the directions, because I have to bring it to this form. Dy dx is 1.3 e minus x minus 2y. So, in this case we will assume that our fxy that is a dy dx is 1.3 this thing into e to the power minus x minus 2y. This is our function differential equation that we will have to solve. So, for dy dx, the Runge-Kutta fourth order method, I am not going into the derivation of it for paucity of time, and you can always look into this at any website, or you can look at it in any numerical method textbook. So, the Runge-Kutta fourth order method takes 4 terms, and this is the expression. Given this dy dx, my task of solving a differential equation is to find a particular y, right. So, what we are trying to do, yi plus 1 is yi, some particular yi plus 1 by 6 followed by a term, and what is that term? k1 plus 2 k2 plus 2 k3 plus k4. This whole thing multiplied by h. H is the again the sampling gap, that is the distance between the individual points that we look at. Now, what is k1? So, k1 is nothing but, when I am taking for yi f x psi yi, that particular function is k1. What is k2? K2 is f of, so suppose there is a curve. Now, I have been given the slope, I do not know the curve. So, I have to, if I know the curve, again the same problem, if I know the curve, then I can find out the value of any particular yi plus 1 given any yi. Now, given any yi, I am trying to guess the curve, right, I am trying to solve the curve. So, xi was here, xi plus half h, I am taking whatever was my h, I am taking half of h, and what is the y part of this function? yi plus half of k1h. Okay. So, because k1 was, k1 was the function that was giving y given an x, that was giving a y for an x. So, I am taking this. What is k3? K3 is again, this part is same, xi plus half h, but this part is now becoming much more predictive. So, it is half of k2h, half of k2, that means whatever has been computed here times h, and k4 is xi plus h, the last one is xi plus h, because I am trying to solve the equation within this zone H. So, xi plus h, I start with xi and this is xi plus h, all right, times k3h. Okay. Here there is no half. Now, this derivation you can look at, but ultimately I multiply it with 1 by 6. So, given this Runge-Kutta formula, let us quickly look at an example. That will be a very nice thing to look at. Suppose a ball is at 1200 Kelvin and is allowed to cool down in air in an ambient temperature of 300 Kelvin. So, the ball was heated and is cooling down. Assuming that the heat is lost only due to radiation, the differential equation for the temperature is given here, this one, all right, where theta 0 we know initial condition is 1200 Kelvin. Find the temperature at T480. So, what is my xi, and so now if I assume a step size of 240, I want to find out the temperature at 480. So, suppose it was at a particular temperature after 480 seconds. So, here is time, it was at 1200 and I have got some radiation formula using which it is coming down. So, I want to find out what would the temperature be at 480 seconds, 480 seconds from the starting point where it was 1200 degree Kelvin. I want to find out this temperature, that is the yi I want to find out given the slope of this differential equation. So, assuming a step size of h to be 240, half of this, if I take half of this 240, then d theta dt, you can compute that here. If you compute the d theta dt is here. So, my formula will be theta I and theta I k1 plus 2 k2 plus 2 k3 plus k4 divided by 6 times h, that is the Runge-Kutta formula, RK formula. So, that is what I want to find out, right. So, now step 1, you see I am not going into all these calculations, but I am finding out the value of k1, all right. I am finding out the value of k2 using this value of k1, k1 is being used here and I find out the value of k2, again the value of k2 is being used here, I find out the value of k3 and k3 is being used here, I find out the value of k4. I find out those values, all right, manually I am doing that now. So, the solution therefore, the approx then theta 0 was 1200 initial condition and here I put in the values of this times h was 240. So, I have taken it at the midpoint. So, I find that the temperature that would be 675.65. That is the approximate temperature at 240, all right. So, this will be the value at 240. Next, I have to find out at 480. So, what would I do? Step 2, I have taken at half point, I found out now my initial value theta 0 is changing. Now, I again do the same thing, find out k1, find out k2, find out k3, find out k4. Now, with this initial condition using the same function, all right. H is again what will be h? H will be again 240 because I have to find it out at 480, right, at 480 degree temperature. So, now I find out that using theta 1 is now 675.65, that is the approximate value that I got earlier, and I compute this. I find out using the same Runge-Kutta method that this is the approximate temperature at 480 degree at 480 seconds would be 594.91 degree Kelvin. Okay. This is how we apply Runge-Kutta method and it's very useful. So, the exact solution of the differential equation is 647.57 if I solve it. Now, it was and we got it how much 594.91 and 594.91. So, it was not very far, okay? Not very far, around 50 degree Kelvin. That is certainly an approximation. So, now we have understood what is Runge-Kutta method. Now, I want to write a C program for it. Again, you might find the approach to be mathematically very novel, maybe intricate, you may find some initial difficulty in understanding, but I am sure you will understand it very fast. But you will see that the encoding it as a C program is or as a program is really simple. Now you are learning C, you can in future you will be using MATLAB and other things, you will be able to solve it very easily. I am showing you the C solution here. On this side, I have kept what we learnt till now, right. yi plus 1, that means in our case the temperature at 480 degree is temperature at 240 degree plus this, and K1 is Fxy, K2 is Fxi, this one Fxi plus half h plus yi plus half K1h, etc., etc., etc. So, now let us look at the program. We have got the math function, everything ready. Now, this function, somehow this function has to be written. Now, this function is here it is being shown as a very simple function. It can be any function, the differential equation function, the earlier function that we have shown, that log function that you have to write. Okay. So, here is an example of a simple function x minus y by x plus y, okay, just for illustrative function. Whatever is your differential, the dy dx given, that will come in this function. So, now you see here I read how many times the h value, x0, x1 value, all these things I read. Now, the key thing comes here. This is the implementation of the Runge-Kutta method. So, very simple. You see I am computing K1, K1 is f x0 y0. So, I am coming to this function computing x0 y0. Then I am going back computing K2 for x0 plus h by 2. H has been read here, scanf h has been read, okay, this h has been read. Then y0 plus m1, I am sorry, here it should be K1, and this should be K2, all these m's you read as K, okay, this is K3, this is K3, this is K2 times h. So, actually we are computing this thing straight away. I am computing all these and then y is assigned y plus kh, sorry, this whole thing is kh. Here this will also be k. So, it will be, this statement will be y will be y plus kh, y plus kh, right, and x plus h, I am incrementing x and going on, all right. I am doing it for 2 intervals till I come over here. So, I ultimately come to this printf and I print the value of y for a particular x. That is the Runge-Kutta. So, this is straight away amenable to some C program, and for each of these f's you are calling the function every time, all right. So, this is the Runge-Kutta method for solving a differential equation. So, I would encourage you to look at other methods of integration, like Simpson's 1/3 rule is a very popular method, and differential equation Runge-Kutta, this is known as Runge-Kutta fourth order method because we are taking 4 terms here. There are even, but this works very well for most of the engineering problems. So, I will encourage you to write programs on this, and later on henceforth we will move to another interesting aspect that is known as recursion, a new style of programming, which we will take up in the next lecture. Thank you.